Hello. In this lecture, we'll study about curves in R3. So R3, it is a three-dimensional space. In a plane, we have studied about curves. So we have studied about curvature of a curve in a plane. And in R3, so there is another degree of freedom. So that's why, so in additional to curvature, we have a concept of torsion. Okay. Okay, so let us begin. So I'll explain all the things accordingly. So let me write down space curves. So my space here is a three-dimensional space. So let us take, so gamma be a regular smooth curve in R3. Okay. And so already we have defined curvature of a curve. So if you have any curve which lies in Rn, so we have defined curvature for that. Okay. So how to define the curvature? So for that thing, so what we have done, we have taken the arc length reparameterization of that curve, and that arc length parameter, it is a unit speed parameter. Okay. So so here also we'll do the same thing. So let us take the arc length parameterization of the curve gamma. Okay. And let S be the arc length parameter. Okay. So as before, so what is the meaning of tangent vector? So tangent vector, so in short, so I'll denote it as T. So T at the point S. So this is nothing but your gamma dot S. Okay. So I have this curve in R3. Suppose this is my curve, and if I take this point gamma S, so this is my tangent vector. Okay. So note that this T, this tangent vector T is a unit vector. Okay. So T is a unit vector because S is the arc length parameter. Okay. So now let us take the curvature. So let Ks be the signed, no, sorry. So let us take the absolute curvature. So let Ks be the absolute curvature of the curve gamma at gamma s. Okay. So what is this ks? So ks is equal to norm of gamma double dot s. Okay. All right. So now, so if I take the derivative of this tangent vector, okay, so this will be equal to gamma double dot s. Okay, and so what we know that this tangent vector, because it is a unit vector, so therefore, so this dot product ts with ts, so this will be equal to 1. This is equal to the square of the norm, so therefore it is the norm is equal to 1, so therefore this dot product is equal to 1. So now if I take the derivative, so twice of this will be equal to your 0. Okay. So note that here, so this gamma dot s, it is nothing but d gamma ds. T dot s is dt ds. Okay. Yeah. So this implies that so t dot s is orthogonal to this ts. Okay. Uh, yeah. Okay. So now let us take, so let ns is equal to, okay, so before that, so let me take this curvature function to be non-zero. So, so assume that the curvature ks is not equal to 0 for all s. Okay. So now, so define an s to be equal to 1 by ks times t dot s. Okay. All right. So this ns, because of this fact that t dot s is orthogonal to ts, so this ns, so this will be again orthogonal to this t dot s. Okay. And what is norm of ns? So this is equal to 1 by mod of ks and norm of t dot s. So t dot s is equal to your gamma double dot s, and we are taking the norm of this divided by mod of okay. So here, yeah. So just 1 minute. Yeah. So here, let us not take this case to be the absolute curvature. So let us take uh, this ks to be the sine curvature, be the sine curvature. So we don't need that this case to be absolute curvature. So therefore, we don't have this thing. Okay. So let case be the sine curvature of gamma at gamma s. So then here, by taking norm of ns, So you are getting this thing. So 1 by mod of Ks. Now mod of Ks is the absolute curvature of gamma. Okay. And mod of Ks is nothing but equal to your norm of gamma dot s. Okay. Yeah. So therefore, this is equal to your 1. Okay. So n is the n is a unit normal vector at gamma s. So ns is unit normal vector at gamma s. Okay. All right. So again, if I go back to this picture, so we have this tangent vector here. Let me draw it again. So we have this 3-dimension space, and suppose we have some curve like this. So the curve is something like this. So we have this tangent vector ts, and this normal vector, it will be orthogonal to this tangent vector. Okay. So this is my definition of an S. So note that there are several unit vectors which is orthogonal to the tangent vector, but we'll particularly take this ns to be equal to 1 by ks times t dot s. So this is my definition of unit normal vector. Okay. So now, so this tau and sorry, this t and n, it uh, it generate a plane. Okay, so that plane, we'll call it to be the osculating plane. So the plane determined by this tangent vector t and the normal vector n is called the osculating plane. Yeah, so this is called the osculating plane. Okay, so now let me define what you mean by binormal vector. Binormal vector. So let us take, so let B to be equal to the vector product of tangent vector with the normal vector. Okay. So we take this thing. So this vector, so the vector BS. So let me write it here. BS equal to TS cross NS. So the vector BS is called the binormal vector. Okay. And because this tangent vector and this normal vector, what we have taken, so they are unit vector. So the vector product will be also unit vector. Okay. So thus, so if I take this vectors, tangent vector, normal vector, and this binormal vector. So this forms an orthonormal basis of R3, is an orthonormal basis of R3. Okay. So again, if we go back to this picture, so I have another vector which is perpendicular to this oscillating plane. So this is my binormal vector. Okay, so at each point, gamma s, we have these three orthonormal vectors. Okay. Okay. So now observe this thing. So first, so check this. So if I take the derivative of this vector product, so this is equal to du ds vector product with vs plus u vector product with dbds. Okay, so this you can do as an exercise. And now if I take the derivative of this b, so b dot, so this is equal to b dot s is equal to t dot s cross product with the normal vector plus the tangent vector vector product with n dot s. Okay, so we have this thing here, and t dot s, we know that it is equal to, from here, it is ks ns plus again this term. And the first term here is equal to 0 because if I take any vector v, so v cross product with v is equal to 0. So therefore this is equal to 0 plus we have this thing. So therefore what we have, okay. So now, so this b dot, so so from here, so this b dot is orthogonal to this tangent vector, and because b is a unit vector, so b dot, again it will be orthogonal to this b, as b is a unit vector. So from that you can show that this b dot is orthogonal to this b. Okay, so this will imply that this, so b dot is orthogonal to the tangent vector t, and it is orthogonal to tangent vector b. And so from here, so this will imply that this b dot, this vector, is parallel to the normal vector n. Okay, so this is parallel to this normal vector. And now let us take, so let beta, so you'll get some real number, let us call it to be tau, such that beta dot minus tau multiplied by n, so beta dot will be equal to minus tau multiplied with n. Okay, so for some scalar tau. Okay, so here we have taken this minus symbol because of some convention which will help you later. Okay, so this tau is called the torsion of gamma. So tau is called the torsion of gamma. Okay, so this tau, it is called the torsion of gamma. Okay. Okay. So this tau, so we have defined it for a unit speed curve. Okay. And so now suppose you have a regular curve. Okay. So how to get the torsion of that curve? So what you do, so you take the arc length reparameterization. Okay. And then it will become a unit speed curve, and then you compute the torsion. Okay. So now, so I'll give you a formula. So how to compute the torsion of a regular curve. Okay. So let me write down. So proposition. So let us take a smooth regular curve with curvature nowhere vanishing. So so gamma be a regular smooth curve in R3 with nowhere vanishing curvature. So it means that the curvature is not equal to 0. So then, so its torsion is given by tau at t. So this is equal to gamma dot t vector product with gamma double dot t. So whole dot product with gamma triple dot t divided by norm of gamma dot t vector product with gamma double dot t, this norm square. Okay, so this is this you have to prove. So then you will get a formula for to compute the torsion. Okay. Okay. So proof. So first, so let us assume that this gamma to be a unit speed curve. So let gamma be a unit speed curve. So first let us assume this thing, and so what we have, okay. Okay. So what we know that this beta dot b dot is equal to minus tau times the normal vector. Okay, so now if I take the dot product both side, so with this normal vector, so what I'll get, so beta dot n is equal to minus tau. Okay, b dot, again dot product with the normal vector n is equal to minus tau. So this implies that, so this tau, this torsion is equal to minus normal vector dot product with B dot. Okay. All right. And okay. And also what we know, so this normal vector, so this is equal to 1 by k t dot. Okay. So which is again equal to 1 by k comma double dot. Okay. So therefore this torsion, so if I put this thing, all this thing here, so what we'll get is the following. Okay. So here also note this fact. So from here, this beta dot b dot is equal to tangent vector product with n dot. Okay. So this is minus normal vector dot product with this vector. Okay, I'm just putting this thing here. All right. So therefore, now what we have, so this is equal to minus 1 by k gamma double dot product with this vector. Okay, so we have this thing here. And now so what is n dot here? So this is basically your ds 1 by k comma double dot. Okay, and again, so this is minus 1 by k gamma double dot product with this vector. So t is gamma dot vector product with 1 by k gamma triple dot minus k prime s divided by ks square gamma double dot. Okay. So we have this thing here, and so now, so this is equal to minus 1 by k square gamma double dot product with gamma dot vector product with gamma triple dot plus k prime s divided by ks cube gamma double dot product with gamma dot vector product with this gamma double dot. Okay. So now note that, so this term is equal to 0. Okay. So why? Because so this one, this vector gamma dot cross product with gamma double dot is orthogonal to gamma double dot. So therefore this dot product, it will be equal to your 0. So this is equal to 0. So therefore, so this is minus 1 by k square gamma double dot product with gamma dot vector product with this triple dot plus 0. Okay. So again, so this you can write as follows. So it is 1 by k square gamma dot vector product with gamma double dot product with gamma triple dot. Okay. So why this is true? So as a vector product with b cross product c, so this is equal to minus c dot product with this vector a cross b. Okay, all right. So now, so this tau is equal to this thing, okay, and uh, yeah, and this. So if I take the norm of this gamma dot vector product with gamma double dot, okay, so this is uh, equal to what? So they are orthogonal to each other. So therefore, this is equal to norm of gamma double dot times norm of gamma double dot. So norm of gamma dot is equal to 1. So this is norm of gamma double dot is equal to this curvature, this absolute value of this curvature. Okay. All right. So we have this thing here. And now what you do, okay. So now if I take, so let us take, so d gamma dt. So t is any parameter now. So let us take any parameter. So this is equal to d gamma ds dt. Okay. And now what you do, so you compute this d2 gamma d2. Okay. So this is basically gamma dot s ds dt. Okay. So this d gamma dt2. So this is what you can show is the following. So this is d2 gamma ds2 ds dt whole square plus d gamma ds d2s dt2. Okay. And this triple derivative, so this will be equal to the following thing. So it is ds dt whole cube d3 gamma ds cube plus 3 ds dt d2s dt2 d22 gamma ds2 plus d3s dt cube and then d gamma ds. So you can show this thing. And after some computation, so what you can show is the following. So this d3 gamma dt3 dot product with d gamma dt vector product with d2 gamma dt2. So this is equal to ds dt to the power 6 d3 d gamma ds3 dot product with d gamma ds vector product with d2 gamma ds2. Okay. So once we have this relation, okay, so therefore, so from here, so what you can check is the following. So if I now take this thing, And okay, so I have to observe one more thing here. So maybe I'll just write it here. So this d gamma dt vector product with d2 gamma dt2. So this is equal to ds dt whole cube d gamma ds vector product with d2 gamma ds2. Okay, so from here, from this equation 1 and 2, so what you can show is the following. So this is equal to d3 gamma dsq dot product with d gamma ds vector product with d2 gamma ds2, and then you divide by norm of d gamma ds vector product with this d2 gamma ds2. So these two things are equal. Okay, and uh, so uh, so from this equation, from these two equations, okay, so this follows from 1 and 2, and from this earlier two equations. So we have this k is equal to, so we know that this k is equal, sorry, this torsion is equal to, this thing. Okay, so therefore this torsion, so this is equal to your the desired result. Okay, so tau is equal to, let me write in terms of dot product, sorry, in terms of this notation. Okay, so we have obtained this formula. So using this formula, you can compute the torsion of any smooth regular curve in R3. Okay, so I'll stop here today.